Hello guys, this is a continuation of my first lecture on the beam column behavior. So this is all about the moment amplification method, which is part of the method 3 of the AISC on stability, K-frame stability analysis. And I'd like to present to you the basis of the formula on the moment amplification factor considered in this first order analysis. So a moment of amplification procedure or analysis is actually a method which takes into account the effect of secondary moments by multiplying a certain factor on the first order moment. So we don't need, so simply by using this amplification factor, no need to conduct a second order analysis. Okay, so no need for a second order procedure or analysis. So consider now a simply supported beam column below. Okay, you can see here the beam column with an actual load and an initial crookedness YO shown below. So in case there's no consideration of any triggering load, transverse load that will trigger an initial bending moment that will cause this to deflect. Okay, so we can assume, and it is a good assumption, that we consider some imperfection, okay, coming from initial straightness or crookedness. Initial imperfection on straightness, or what you call crookedness, YO. So if there's an initial imperfection, then buckling will begin, no? Buckling will commence, and this will cause your P to your actual load P to take advantage of the situation, causing the beam to reach its critical buckling load. So YO in this regard can actually be considered as an initial sine function. So this is a sine curve, no? So this graph here, this graph is initially will form a sine curve. So this is how Euler differentiates buckling from simple bending moment. Now we're in the approximation functions considered for your elastic curve is a polynomial curve rather than a sine curve. Okay, so YO is simply a function of the angle considered. So this is what? This is a half sine wave. Okay, half. So as a sine wave, a full sine wave is like this. So we only consider one half of this as your part of the initial curve here. So if you define this is simply a function of an amplitude multiplied by the sine of an angle, which is the the angle defining your period. Okay, so this defines your frequency or period T, okay, or your frequency F, and this defines your amplitude or your simply your maximum height here. Okay, so this is the amplitude A. So this is now an A sine x. Okay, and A is simply the maximum amplitude, which is E. So this is the maximum amplitude A, and your angle here, which is has something to do with the period, okay, is simply uh, defined in terms of pi x L. Okay, so if you do an analysis or a graph analysis of your sine wave here, you will notice that the uh, the length of this is simply your pi. So if I make use of a substitution on the value of x in terms of the length, the total length L of the beam. So if I substitute L here, this will become pi L over L. What will remain here is only your pi angle there. Okay, so that's why this is now your representation of your YO, where E is the maximum initial displacement, and we recall the moment curvature relation from our beam problem. Okay, this is the Euler-Bernoulli beam equation. Okay, negative m. Again, the negative sign is there to indicate only that the deflection is going downward, opposite your right-handed system here for your y. Okay, so what is your bending moment? This is the bending moment m is caused by your eccentricity E. Okay, in this particular initial curve, but in the final curve here, wherein your uh, uh, bending is amplified because of your P times YO, okay, the P delta, the secondary moment. So your moment equation now becomes P times the total, okay, the total okay, deflection YO plus Y here. So this is P quantity YO plus Y at this point. So this moment here refers to a section coming at this point where the distance is equivalent to x. So substituting this in our Euler-Bernoulli equation or the moment curvature equation, so we have this one here, where YO is inserted in terms of this sine wave and Y is still your Y to be determined. Okay? So taking and rearranging your equation to form a differential equation which is non-homogeneous because the right hand side is not equivalent to 0. So you call this a non-homogeneous differential equation. So this is the acronym of NHDE. But we all know that a differential equation can be solved. A non-homogeneous differential equation can be solved by considering first the homogeneous part, solving a solution on the homogeneous part, and then adding it to the particular solution. And we know that the homogeneous solution is a simple what cosine or cosine sine function, wherein the frequency, you call this now the frequency or the of the angle x is defined by the coefficient of this. Okay, so if we do the long method here for this, so if you use the characteristic equation, you can just make use of the root. No, so this is a squared derivative, or a second order derivative is an m squared plus or minus, or this is I think plus. That is minus. Okay, that's minus p over ei equals 0. So you take the homogeneous solution first. So this is the homogeneous. When you say homogeneous, the right hand side is always 0. Okay? A homogeneous solution is your RHS is 0. Okay, a non-homogeneous equation is that the right hand side is not equal to 0. So if I take now my root, m is simply equivalent to the square root of p over ei. I think this is negative, that's why positive siya. This is positive, sorry. So this is an imaginary. This is a negative p. Yeah. So my roots here are plus minus the square root of p over ei times I. There's an imaginary there. Okay, so when the root is an imaginary root, we know that the solution is always okay. The solution is always a trigonometric solution. Can always be a trigonometric. If this is not an imaginary root, it's a hyperbolic solution. But both can be solved using exponential solution. But we do not use this, no? So we don't use the exponential, we use the trigonometric as your solution. Hence, by applying the values on the boundary condition, so at the boundaries, you will take note that this equation is what? Is 0, no? The deflection at the boundary. So y is 0 at the boundary. And the boundary is referred to the ends, no? The end points of the beam. So at x equals 0, cosine of 0 is 1. At x equals 0, sine of 0 is 0. So we have an equation 0 equals a plus 0, therefore a equals 0. Apply boundary condition 2 on L. So at x equals L, that this is 0. So this is now 0. So what will remain is b sine of square root of p over ei L. Okay, b cannot be equal to 0 because this is a coefficient that will make your solution non-trivial. So this is now the one that is equated to 0. But the sine of an angle equivalent to 0 is always a multiple of pi. Okay, so wala yung sine dito, no? So remove that. The angle is always an n multiple of pi, 0. You call that n equals 1, n equals 2, n equals 3, etc. Okay, so all the sine of this angle are 0. And therefore, we take the value of the first at n equals 1 then P is equal to pi squared EI all over L. So the particular solution now will give you a form similar to this form here, no? So the particular solution always follow the form of the uh, non-homogeneous right-hand side. So this is the form, constant multiplied by the sign. So this is now a constant multiplied by the sign. We cannot choose the constants a and b because we have already used them. So c sine pi x over L. So we just add, no? We just add it here. So y is simply this and this particular solution. Okay, so take note that the total solution is simply equivalent to the homogeneous solution plus the particular solution. Okay, so if we substitute it here, the values of A, so this will now be extracted, 0. So we'll start at B sine, where B is not 0. Okay, so your final solution now will form this one. We substitute equation 4 in equation 3 here. So where is your equation 3? This one here. Okay, so we substitute it here, and our intention is to get the value of C first in order for us to be able to finally compute for your particular solution later. Okay, so if I substitute now this solution here, so this is simply negative pi squared L squared, because we differentiate this twice. So the derivative of sine 2 times is sine, but it will be negative, no? So this constant pi over L will be multiplied twice. Okay, so negative pi squared over L squared C sine. Okay, the next equation here is simply a y. So we simply substitute the plus y. So this is simply y. Okay, so this is d squared x y, okay, plus p over ei y. Okay, so p over ei y is equivalent to the non-homogeneous part here. Okay, so notice that all the equations have a sine pi x over L. So we can cancel all the sine pi x over L there. So what remains is C can be factored out, no? Here, C can be factored out in P over I minus pi squared over L squared. Okay, so that's the denominator, put it here, and this is the numerator above. Okay, therefore some cancellation on EIs. If I make this P over EI, so I cancelled P over EI here. So I place, what I did here is I place P over EI below here. No? So I place a P over EI. Okay, so what remains is the negative. So I remove this. The negative E will remain there. Okay, and then if I divide this P over EI divided by P over EI, it's a positive 1. And then this divided by this is this one. Okay, so this is now my value for C. And substituting the value of C in my equation, so this will be the form of the equation I want. Take note that my PE, the P here is assumed to carry the critical load, which is the Euler buckling load. Okay, so that's why this becomes now a PE over P instead of a P over P here, instead of a P over a P. Okay. So this is pi squared. Okay, so this is actually your critical buckling load, PE. Sorry, class. So this is not. Okay, so P is the applied load actually. So what happened? Yes, this is now your PE. What happened? Why this came from here? Because this is the negative sign was removed. Okay, so the negative sign was removed there. That's why this interchange, no? So this becomes the first expression, then -1 there. So just a clarification on that. Hence, your y now is simply this times sine pi x over L, and substitute this equation into equation 2, our moment. No, so remember this is the yo plus y. Okay. Okay. So the maximum moment now occurs at L over 2. Hence, if we know that the maximum moment is always at the midspan for a simply supported end or pin ends, then this will give you a value at x equals L over 2. Okay, so this will be substituted in this. That's why this becomes pi over 2. Okay, the sine of pi over 2 is 1. Okay, 90 degrees. Okay, sine of pi over 2 is 1. Okay, and also here, the sine of pi over 2, we substitute pi over 2 here, is also 1. So this becomes now e plus e over p minus 1. Then at the point of maximum location, the moment by simplification will yield to this. Okay, wherein your PE here is simply equivalent to MO, and MO is what you call the unamplified moment coming from the first order analysis. Okay, so this is now your magnification factor as described on this. Okay, so for LRFD, your P can be substituted in terms of PU, hence the amplification factor considering LRFD form is simply this one. But this is not yet the exact formula to be used on some conditions, but this is already the basis for the AISC LRFD amplification factor, which is equation 6 of this lecture. Thank you very much for listening. I'll see you for the continuation of this video.